For a very long time, a species on a small blue planet on the outskirts of a galaxy, like hundreds of billions of others, has been peering into the infinite universe. Human beings ponder whether life on Earth is unique.
Our position, in space at least, is not remarkable in any way. We might ask whether this applies not only to Earth, but also to man as a living being.
We have scoured our moon and explored every canal on Mars. Our probes traverse the solar system, scrutinizing every star in their path. And our telescopes detect increasingly remote planets, newfound worlds around distant suns.
We've discovered close to 6,000 now. We want to characterize them. We want to find out what's out there.
We are on the brink of discovering another Earth. But will it be inhabited? As scientists continue their journey across the Milky Way, massive installations on Earth are being harnessed to achieve an even more lofty goal: to intercept communications from extraterrestrial civilizations and attempt to establish contact.
We are looking for a signal that carries information.
We've already sent quite a few signals into space, so if anyone is watching, they will have seen us.
No form of life can be ruled out. Space agencies all over the world are scouring the galaxy for anything from the tiniest bacteria to an advanced civilization.
Some of the destinations that we think could harbor forms of life are actually not the other planets in the solar system, but some of their moons, specifically their icy moons.
How can we identify habitable and inhabited worlds in the vastness of the universe? How can we detect a form of life we don't even know exists? How can we communicate with extraterrestrials we know nothing about? And might they, too, be looking for us? All over the world, scientists are pooling their efforts in the hope of one day answering a question that preoccupies humankind. Are we alone in the universe?
The universe is a pretty big place. It's bigger than anything anyone has ever dreamed of before. So if it's just us, seems like an awful waste of space.
For thousands of years, man has been gazing at the skies. The movement of celestial bodies has allowed us to measure the passage of time, draw up calendars, and schedule the cultivation of the land. This world passing over our heads guides our life on Earth, our beliefs, our religions, and the position we think we occupy.
Since ancient times, our view of the world, or rather the Western view of the world, has placed the Earth at the center of the universe, with all the other celestial objects, the moon, the sun, the other planets, the distant stars revolving around it.
How could we possibly think any differently? When we walk, the ground is motionless beneath our feet. When we look up at the sky, the sun is moving around us, and not the other way around. Only by close observation have we been able to see beyond appearances. In the 15th century, scientists were able to study the skies for the very first time. The arrival of the first telescopes changed everything. New moons were suddenly visible, but this time they revolved around Jupiter, not the Earth. It turns out we are not the center of everything after all.
The Earth was dethroned from its privileged position. The Sun was now placed at the center of the world, with the Earth relegated to the rank of just another planet.
Copernicus, Galileo, Newton, and others paved the way. Nothing would ever be the same again. After the Sun displaced the Earth from its celestial position, we then discovered in the early 20th century that the Sun itself was far from being the center of existence. In fact, it's hurtling through space at over 850,000 kilometers an hour, taking us with it in its mad rush. In the end, It's just one star among many, lost on the outskirts of a galaxy containing hundreds of billions. And the head-spinning numbers don't stop there. Our galaxy, the Milky Way, is just one of thousands? Billions? Hundreds of billions? It's hard to imagine a world with no end. Everywhere we look, we see galaxies and stars. Between 2003 and 2004, scientists pointed the Hubble Space Telescope at a dark area of the sky, a tiny black square wedged between a few stars. After holding the exposure for 1 million seconds, new lights appeared. Each of these dots is a new galaxy, never seen before. After analysis, scientists counted 10,000 of them, 10,000 clusters, each containing billions of stars, in an area of the sky you could cover with a pinhead at arm's length. For the great science fiction writer Denis Bajram, these discoveries haven't brought us many answers, but they also leave us with existential questions.
There was a degree of comfort in ancient times when Earth was at the center of the solar system, the center of universe, of creation. It meant it had all been created for us. It was the destiny of our planet, with probably each individual on it having their own personal destiny. Suddenly finding yourself located on the outskirts of a galaxy, itself lost in a universe containing billions of galaxies, brings with it a certain amount of insignificance. We are reduced to a speck of dust in the cosmos. It's Copernicus's principle of mediocrity. Our position in space, at least, is inconsequential. And one is given to wonder whether this applies not only to Earth, but to man as a living being.
Given the full potential of the universe, all the stars, all the planets, all the galaxies imaginable, how could we possibly be regarded as exceptional? The hypothesis simply doesn't hold. According to calculations, the observable universe comprises 100 billion galaxies at the very least, each containing 100 billion stars, most of them surrounded by planets. All in all, it's 10,000 billion solar systems or potential worlds. That's the figure, 1 followed by 22 zeros. Being alone, then, in the cosmos would seem scarcely credible. A 1 in 10,000 billion incidence. So if our solitude is unlikely, all that remains is to find signs of other life.
Philosophically speaking, if we were to find life outside of our planet, what does that mean for humanity? What does that mean for politics or world religions? It has the power to completely turn upside down human understanding.
As time goes on and science progresses, the possibility of finding life elsewhere and of investigating extraterrestrial encounters is becoming an obsession for many minds, among them the most brilliant.
Enrico Fermi was a great Italian physicist, winner of the Nobel Prize in Physics, and probably the last great physicist who was as good at experimentation as he was at theory. In 1950, over lunch at Los Alamos, the laboratory where he'd worked during World War II on the Manhattan Project, he asked the famous question, "But where is everybody?"
First of all, Enrico Fermi pointed out that for pragmatic reasons, there was no point in looking at the universe as a whole. The dimensions are immeasurable. Take the simple distance separating our galaxy, the Milky Way, from its very close neighbor, Andromeda. two galaxies among hundreds of billions, separated by a distance of 2,500,000 light-years. Meaning that traveling at the speed of light, the fastest thing in the universe, it would take us 2.5 million years to reach Andromeda. For us mere humans, other galaxies are unreachable horizons. In the quest to find other life, we must confine ourselves to our own little cosmic island. And the Milky Way is already a huge playground. Starting from this observation and returning precisely to the question, are we alone in the universe? Fermi was actually asking why, here in our galaxy, extraterrestrials aren't already there right in front of our eyes, or even already among us.
Imagine that this tree represents the Milky Way, and each leaf represents a star. And on one of these leaves, a civilization appears, one that has reached the technological stage whereby it is able to master interstellar travel. And this civilization spreads throughout the Milky Way by exploring the stars, first in its intermediate vicinity, then little by little the whole of the galaxy. If we do the math, we can see that after a few tens of millions of years, this civilization will be able to explore the entire Milky Way. And then the question arises, but where is everybody?
For Fermi, it was a veritable paradox. 150 million years ago, there were no flowers on our planet. 3 million years ago, humans, in the broadest sense, did not yet exist. In 800,000 years, we've gone from mastering fire to taking our first steps on the moon. Among the hundreds of billions of stars in our galaxy alone, and over the 10 billion years of its existence, it's more than likely that at least once, an extraterrestrial civilization has developed and flourished somewhere, and one day managed to master the journey between two stars. If that is the case, it would have taken them only a short time to colonize everything, and they would already have passed through Earth.
They should be here by now. They've had plenty of time since our sun arrived relatively late on the cosmic scene, while at least half the stars in the Milky Way appeared much earlier. So it begs the question, which gives us the famous Fermi paradox.
70 years on, Fermi's question is still relevant. We cannot be alone, and yet, until now, signs of extraterrestrial life have eluded us.
So Fermi would argue, if there was life out there, surely we would have found it by now. But perhaps other forms of life has found us, but they haven't made contact, or we haven't detected it, or perhaps alien life did find us and thought, we better leave them alone.
There's no shortage of hypotheses to explain the lack of contact, but it must first be acknowledged that while aliens have not yet deigned to visit us, we ourselves are in no position to seek them out.
3, 2, 1, 0.
Our most distant space probes took around 30 years to leave the solar system. At that rate, it would take them 20,000 years to reach a nearby star and 500 million years to cross the galaxy. To move forward in our quest, we should instead concentrate on what we do best, observing and understanding the skies with mind-boggling precision.
For that one fraction of a second, you were open to options you had never considered. That is the exploration that awaits you. Not mapping stars and studying nebula, but charting the unknown possibilities of existence.
Once we accept that it is possible to observe the universe around us and to look for signs of life or clues to the presence of life, we should harness every possible means at our disposal.
If we want to track aliens across the galaxy, we need to examine the skies methodically. If we can't reach distant stars, we can at least see them and study them through the light they emit, dissecting it in minute detail. And unlike our ancestors, we are no longer restricted by our eyes. We know that light takes the form of a wave traveling at 300,000 kilometers per second, and more importantly, that it oscillates, vibrating at varying speeds. This frequency of vibration produces the different colors we perceive, from violet through to red. On the other hand, light sometimes vibrates so fast that we can no longer see it. As is the case with ultraviolet, X-rays, and gamma rays. Likewise, light can vibrate too slowly to be visible to our eyes. As with infrared, microwaves, or radio waves. In these latter cases, it is still light, albeit invisible light.
To observe waves that are not visible, we need instruments that can contemplate or replace our eyes and detect this invisible light. Infrared sensitive, radio sensitive, ultraviolet sensitive, X-ray sensitive, etc.
Technology has enabled us to go beyond the limitations of our senses. Today's instruments take the form of ultra-modern telescopes perched on mountains. Some deploy mirrors in the middle of the desert, while others are sent thousands of kilometers from Earth to send back extraordinary images. We see farther, but also differently. The sky reveals itself in a whole new light. By observing new light frequencies, we can even detect new planets and new worlds. But let's not get ahead of ourselves. Our search for life throughout the universe begins with the study of a very specific range of the light spectrum: radiometric waves, a particularly extended, non-visible form of light. Philippe Zarka is one of the world's leading specialists in radio astronomy. At the Paris Observatory, he works on the ever more finely tuned detection of these radio waves.
We are bathed in radio waves. They pass through the atmosphere to us on the Earth's surface, but are extremely faint. The processes in the universe that produce them do so quite weakly. So, to detect them, we need very large instruments that concentrate the light using curved mirrors to focus the signal so it can be detected and analyzed to determine its information content.
At Nancy, in the middle of the Sologne forest, the Paris Observatory operates one of the world's largest radio telescopes. This incredible metal infrastructure extends over almost half a kilometer. At each end, gigantic steel meshes act as mirrors for radio waves. Their purpose is to redirect the signals coming from space and concentrate them towards the focal point at the center of the structure for analysis. It's a play on geometry as simple as it is vast.
The light rays hitting this mirror are reflected horizontally, parallel to the ground, before striking the primary mirror, which focuses them on the focal point of the system where the radio waves are transformed into an electrical signal, which can be analyzed to determine what information it contains.
This precise analysis of electromagnetic radio signals from the farthest reaches of the universe makes it possible to discover the hidden phenomena agitating our cosmos. Within the Milky Way, clouds of interstellar gas and dust reveal new facets, while mysterious stars like strange pulsars appear before our very eyes. But if radio waves are emitted throughout the universe by all manner of stars and phenomena, on Earth, their great interest lies in the fact that we have been able to domesticate them. For a century now, radio waves have enabled us to receive, yes, radio, but also to interact with GPS and communicate on a large scale with our smartphones. Might an extraterrestrial civilization do exactly the same?
He's home from...
For the last 100 years, we've been sending radio signals around the Earth to communicate, to inform, to entertain. These signals travel all over the planet and beyond. Once transmitted, they also spread in all directions, leaving the Earth at the speed of light. That's to say, 300,000 kilometers per second.
We've already sent quite a few signals into space, starting with all our radio and TV broadcasts. Our entire existence is out there, carried through the universe on our airwaves. So if anyone is watching, they've seen us.
Could aliens, wherever they may be, have made the same choices as we have? If we assume that physical constraints are the same throughout the universe, it's very likely that any extraterrestrial civilization, at least as developed as ours, has chosen radio waves to communicate.
These waves are easy to produce and detect using relatively simple technologies.
So could we, in theory, detect an extraterrestrial television broadcast? Or a telephone call? It's not that simple. Our terrestrial communication waves are emitted in all directions, but fade rapidly with distance. Once in space, they become difficult to detect. The same applies to any extraterrestrial civilization. On the other hand, it is possible to considerably increase the range of these signals by focusing the beam, concentrating it in a single direction and powering it out to the stars. So let's hope that a technological civilization opts to undertake such focused transmissions in our direction with the aim of communicating with us.
I observe the universe winking.
How can it be happening?
Can't.
For over 50 years, radio telescopes around the world have been scanning the skies in the hope of detecting such an initiative. An extraterrestrial message sent in our direction, even though their planet would remain undetectable. But if an intelligent signal were to reach us, would it be perceived as such? The billions of stars that populate the universe inundate us with all kinds of radiation. Even if we limit ourselves to radio waves, which are ideal for communication, a veritable cosmic brouhaha is taking place above our heads.
We are looking for a signal that carries information. One extremely simple way of sending signals, for example, is Morse code, which is dots and dashes. One beep will mean something, two beeps something else, then three beeps, and so forth. Meaning you have to modulate the signal. You need to make strong signals, zero signals, weak signals, etc. If a steady, unvarying, unchanging radio wave is sent out, we could detect it, but it wouldn't carry any information. So what we want is to detect a modulated signal over time.
In 1967, a mysterious signal aroused curiosity when a perfectly regular pulse reached us from a fixed point in the sky. In fact, it was the first pulsar ever discovered. An ultra-dense star sending intense radio flashes in our direction like a metronome. In 1977, another astonishing signal reached us, dubbed the WOW signal. However, it could not be identified with anything currently known and would never be repeated, so it was hard to know what to make of it. After 5 decades of careful celestial observation, we have yet to detect anything convincing. Faced with this dearth, we humans are trying to break the silence of the universe.
Conversely, we figure that since that's what we're looking for, then maybe we should do the same for any extraterrestrial civilization that might be looking for radio signals from us. So the idea is to send out signals through radio telescopes, transmitting them from the focal carriage to hit the spherical mirror, which in turn will reflect the signals horizontal towards the moving mirror, which will then send them in the direction of the corresponding area of sky.
For decades, we've been sending out our own signals to any civilization potentially capable of detecting and decoding them. Simple logical sequences, mathematical answers, enough to prove our intelligence to the entire universe. Or at the very least, show to anyone who might pick them up that the signals could not possibly be random. Despite these many attempts, the silence is deafening.
I find it hard to believe the hypothesis that a civilization might be developed enough to be aware that it exists within a galaxy and yet not want to transmit something like we did. So why the silence? Maybe our radio telescopes aren't pointing in the right direction. The galaxy is vast, and there are billions of stars around us. Maybe our detectors aren't sensitive enough, and we're not detecting weak signals. Maybe we're not listening at the right moment, or their radio signals haven't arrived yet, or they've already passed far from us at the speed of light. Or maybe they've been disappointed by not receiving any response.
We should not be discouraged by this lack of detection. We are without doubt still in the early stages of our quest. A few decades of observation are nothing in the history of our civilization, and even less in the life of the cosmos. Take our transmissions as an example. The oldest are at best a century old, so they've been spreading across the universe at the speed of light for 100 years. They are now 100 light years away, 1,000,000 billion kilometers. That sounds like a vast distance, but it's only our immediate galactic neighborhood, a few hundred stars and their planets. 100 years from now, those first signals will have continued to travel, reaching a bubble 200 light years away. Then in 1,000 years, they will have traveled 1,000 light years and still only covered just 1/100th of our Milky Way. But supposing someone hears from us 1,000 years from now on a planet located in this small corner of the galaxy? If they answer right away, we'll need to wait another 1,000 years for the reply.
Let's imagine we receive a signal. Beep, beep, hi, I'm Beep, beep, the extraterrestrial. I've sent my signal. In fact, the signal may have left 10,000 years ago. Is there still someone there 10,000 years later who could respond? Our reply will then take another 10,000 years. Will there still be anyone there 20,000 years later to hear our message? And in 20,000 years' time, will we be able to respond to any message sent?
Even within the galaxy, even at the speed of light, the distances are gigantic. To communicate, we'll need to be patient and be able to endure. The longing for an encounter or a possible communication. Lulled by science fiction, we imagine extraterrestrials as a civilization at least as technological as our own. But when considering life, whether here or elsewhere, it is not the only factor. Far from it. To advance in our quest, we need to consider life in the broadest sense. The same living world that abounds us, one of unprecedented richness that doesn't seem to communicate through space. We ought to be able to detect such living things directly with the help of tangible observations.
1,500 years ago, everybody knew the Earth was the center of the universe. 500 years ago, everybody knew the Earth was flat. And 15 minutes ago, you knew that people were alone on this planet.
Imagine what you'll know tomorrow.
Until now, we logically assumed that the presence of billions of stars around us also implied the existence of billions of planets. But we had no proof of this. Not until 1995 was a planet around a star other than our own finally detected. The first confirmed exoplanet, 51 Pegasi b, a giant, gaseous planet similar to Jupiter.
That was really unique because we finally knew that there is planets around other stars as well, and the solar system is, luckily, not as unique as it would be otherwise, not as we might have thought before. And with this discovery, we knew we can go for a lot more.
Despite advances made in telescope technology, planets were still very dark objects, difficult to distinguish from their dazzling stars. Detecting the first, and those that followed, with 100% certainty required state-of-the-art instruments, along with a bit of cunning.
So one of the most exciting and one of the most efficient methods actually we do have to detect exoplanets, so planets around other stars, is the so-called transit method. So the transit method can be explained actually in quite simple terms. If I take, for example, a coin out of my pocket and put it in front of the sun, it's all what we need to have a look at and what we need to face. So the coin is moving in front of the sun, and by that movement it's blocking the sunlight by a bit, and we can measure this tiny little bit of blocked light with very sensitive instrumentation. And it's also a bit like a solar eclipse, for example, or we can also compare it to a Venus transit or Mercury transit, where Venus and Mercury seen from the Earth are moving in front of the sun. It's just like exoplanets transit in front of their host stars.
In the wake of the first discovery, dozens of scientific programs began to tackle this new field of research. When space telescopes were launched, first dozens, then hundreds, then thousands of other planets were discovered around us in our galaxy.
We are at 5,919 exoplanets in the meantime, so approaching the 6,000. And I'm regularly giving talks on the topic as well, and I'm updating that number on a regular basis as well, and it's really growing from day to day.
The question now is, what do these planets look like? What worlds do they conceal? And above all, are they capable of supporting life? To find out, our telescopes are on the lookout for the slightest piece of information. When a planet passes in front of its star, the amount of light it blocks out allows us to guess its size. On its second pass, the length of its orbit can be deduced. Then, by closely watching the movements of its star, other instruments can gauge its mass. The plot begins to thicken. We can now estimate its density and composition, the distance at which it orbits its sun, and the heat it can generate. Trawling through the analyses provides a glimpse of unimaginable worlds, planets where iron rains down from the sky. Others where the temperature between day and night varies by several hundred degrees, or giant balls of burning gas. But beyond these hellish worlds, what we really want to find is a new paradise. Among all these fabulously exotic worlds, we are now looking for a planet similar to our Earth. A small, rocky planet located at a safe distance from its star, where the temperature is just right for liquid water, for example.
It's hard to imagine a life form living in a vaporized, molten metal, but we need to be prepared for unexpected surprises. Often, when we talk about habitable planets, we mean habitable for us. Ideally, there would be water, oxygen, and of course a little vegetation, and preferably a bar at the end of the street from which we can watch the lake while on vacation.
To pinpoint this paradise and be certain of its existence calls for even more in-depth analyses. And the entire scientific community is pooling its efforts in this quest. Each new planet needs to be examined in minute detail. On the ground, radio astronomers, the same ones that were looking for an extraterrestrial message, compete inventively to maximize the sensitivity of their telescopes. Increasingly mind-boggling installations are being built, some stretching for miles. These antenna fields can still detect invisible electromagnetic radiation, except now it isn't a matter of picking up some kind of communication, rather the particular signals emitted naturally by certain planets, the ones that boast a magnetic field. In other words, a kind of magnet capable of repelling certain threats.
It's very interesting. I'd like to measure the magnetic fields, the aurora of these planets, because a magnetic field means a protective shield against the bombardment of the planet by energy particles in a solar wind from its star. Such protection can be a favorable factor for the development of life.
Our planet's magnetic field on Earth has protected us for billions of years from our star's immense jets. This protective bubble deflects high-energy particles, sometimes creating the magnificent auroras we see at the poles. Finding other planets with similarly protective magnetic fields would be excellent news in the search for extraterrestrial life. But it's not enough. The Earth is also habitable and inhabited because it has something else essential to life. An atmosphere, one that is rich in oxygen in particular. This is at the very heart of Teresa Luftinger's research and the Ariel space mission she is helming. Ariel is a telescope that will be placed in Earth's orbit in 2029. Once in space, it will be able to analyze the atmospheres of distant planets to determine their composition and reveal whether they contain elements essential to life as we know it. Air similar to our own. But that's not all. As more and more readings are taken, we could finally reach the Holy Grail. Imagine that over several years of observation, the composition of an atmosphere changes. Say the CO2 content varies, for example. That could be due to the presence of bacteria, plants, or even animals modifying their environment.
It's a very, very interesting, exciting development that happened in the past few years in astronomy, actually, in astrophysics as well, is that a lot of different topics came together, like geology, astrobiology, biology in that sense. We need to understand each other to really find out more and to understand what's going on, what kind of physics you need to change from a dead world to a habitable one.
In space, no one can hear you scream. Yeah, but I mean, some people might think that we're better off alone, that if an alien race was to encounter us and it wasn't so friendly, that it's better that they swerve Earth and they don't find us and they don't enter into conflict with us. Or perhaps they are peace-seeking and we can learn a lot from other civilizations. We just don't know.
In this scene, I was drawing a sort of congress of aliens from very different planets. So here, for example, we see a very small one in a jar. It has a sort of articulated robot, so it can mingle with the others. But I was also thinking there might be some that are 100 meters long, adapted to very low gravities that couldn't make it to this congress. The variety of shapes is something we can't get our heads around because we already are stuck with our earthly vocabulary. Looking back on this particular panel, where I've tried to be extremely varied, with years of hindsight, I still don't find it varied enough. The limit of life in the universe isn't life in the universe, it's our imagination.
For a clearer idea of the possibilities of living organisms across the universe, we must first study them in detail here on Earth. This is the role of Nicole Kaplan, an astrobiologist with the European Space Agency.
So we've come here to the sand dunes of the Netherlands, and now on first glance it might look like quite a dead place. I mean, we're in the middle of winter and you can see that there are plants, but there's not much greenery. But if you take a closer look, for example, on this tree here, you'll see that it's actually covered in these beautiful lichen. And what this means is that there's actually so much life that is contained in just this one area. So if you were to take just a little piece of lichen and you were to put that under a microscope, you would then see such amazing life forms.
Clearly, even in seemingly inhospitable environments, life will always find a way. The aim of astrobiologists is to take this reasoning as far as possible, to strive to understand the most extreme contours of life on Earth before tackling the question of life elsewhere.
There's a reason that we want to understand the limits of life in the context of astrobiology, and that's because if we're going further away from Earth and we're searching for other life forms, we're going to need to know what we could possibly find. And if you look really closely to very hostile environments that we have here on Earth, and I'm talking about the deserts on Earth, I'm talking about the deep oceans and Antarctic and Arctic conditions, there is life in these environments.
If life is possible in these extreme terrestrial environments, why not in the frozen caves of Mars? Or the searing heat of Venus? And why not go even further? Imagine life in the most inhospitable environment we know. In the icy vacuum of space. That's the aim of the EXPOSE experiment, a mission that can call upon an extraordinary laboratory.
So the EXPOSE payload's purpose was mounted to the outside of the International Space Station, and it was used as an experimental setup or testbed for exposing biological organisms to the entire space environment outside of the International Space Station. Some of these organisms were plant seeds, some of them were lichen, fungi, and various species of bacteria, archaea. And they told us a lot about how life responds to the space environment.
The initial results are surprising. Most of these organisms, although derived from life on Earth, appear to be far more resistant to the hostility of space than we thought. Whether it's radiation, microgravity, or changes in atmosphere. This finding is far from insignificant. These plants, microbes, and bacteria are the basis of all life on our planet. Could they be the origin of other life? Life elsewhere? Life adapted to conditions radically different from those we know on Earth. Life that might develop way beyond what we could imagine.
It may be that, unbeknownst to us, there's a network of thought between all the bacteria on Earth, and that it's actually the planet's highest life form, one that's already in communication with other life forms. We have a single horizon that stops at our scientific knowledge, which is immense yet feeble.
Far from fantasy, these very pragmatic discoveries reveal an extremely wide range of possibilities in terms of living organisms. Microscopic life that is capable of flourishing anywhere, and perhaps much closer to home than we thought. The real, scientific, tangible hope of extraterrestrial life could lie in our own solar system, where the first fantasies of life on another planet first began.
That's a Martian. I'm not going to have that thing in my house.
Our love of little green men no doubt stems from our long-standing desire to find another life form, preferably one that's accessible. Life on the planets and stars closest to us, within sight and within rocket range. 150 years ago, the earliest maps of Mars, our nearest neighbor, hinted at artificial canals. Surely the work of the famous Martians. Today, we've studied the red planet from every angle, and rovers have been scouring its surface for decades. They provide us with breathtaking images, but signs of life are still elusive. But in recent years, the search for life in our solar system has been in full swing. In this close suburb of our planet, entire worlds have yet to be discovered. In fact, it has become a priority among the world's leading space agencies.
Some of the destinations that we think could harbour forms of life are actually not the other planets in the solar system, but some of their moons, specifically their icy moons. Having a moon isn't something that's unique to our planet Earth. In fact, if you look around the solar system, there are many other planets that have multiple moons.
Our natural satellite is far from the only moon in the solar system. Mars is accompanied by Phobos and Deimos. Neptune has some 15 moons around it. Saturn has at least 24 regular moons. As for the giant planet Jupiter, 57 have been named. And some of them are even larger than planets. We now know them to be icy, inhospitable worlds, at least in appearance.
Saturn's moon, Enceladus, Jupiter's moon, Europa. These are destinations that are highly scientifically interesting because there could be life beneath the surface. And what I mean by beneath the surface, these are icy moons. So you can imagine that they are completely covered in ice. But if you go maybe not even 100 kilometers deep below the subsurface, you might then find a liquid ocean which is teeming with life.
The presence of liquid water is undoubtedly essential for life as we know it. But it's not the be-all and end-all. Despite their vast distance from the sun, a second phenomenon could work in favor of these worlds. Whether Saturn or Jupiter, these planets are so gigantic, nearly 1,000 times larger than the Earth, that their mass causes extreme tidal phenomena on their moons. Internal stresses and friction could generate a source of heat essential to life. The plot is thickening around these icy moons. Their subterranean oceans may be teeming with bacteria and microbes, or at least contain the first elements of life. It's time to take a closer look. Unlike distant exoplanets, the great advantage of Jupiter and Saturn's moons is that they are accessible to the probes we've been sending out for many decades.
So a very exciting mission that the European Space Agency has launched last year is the JUICE mission. And this is set to arrive around Jupiter in 2031. JUICE will be loaded with a plethora of scientific instruments to learn so much about the icy moons in particular. There will be an ice-penetrating radar, and this is a very interesting instrument because this will tell us what is beneath that surface of ice, what's beneath that layer of ice, and gives us a much more high-resolution look at a subsurface ocean that may have life.
Within just a few years, we may well discover the first form of life within our own solar system. Even microscopic, even primitive, it would represent a giant step forward for mankind.
It could mean that life has developed on both planets independently, which would be very encouraging because if it happens independently on two different planets here, it could happen elsewhere. This would be much more encouraging for the existence of life on an extrasolar planet.
Malcolm was right. Look. Life found a way.
Science is providing us with increasingly powerful tools and ever more inventive methods. Our eyes are sharper than ever, and our progress is exponential.
If we detect a planet that seems to be very similar to Earth, and we indeed discover oxygen, methane, and water in the atmosphere, we maybe even see changes with the orbit of the planet around the star. That would be very exciting, certainly.
Maybe we'll have some answers about our closest planetary neighbours, or maybe there'll be some surprises that come online after looking at data from telescopes in deep space.
The quest for other life is no longer a fantasy. It is now a scientific reality. In the coming years, the first extraterrestrial bacteria may be discovered. In the coming decades, whole habitable worlds may be revealed to us. And before we can actually reach them, we may have to wait hundreds or even thousands of years. On that day, we may be the first to make the journey to other suns. One thing is certain, the technological civilizations that populate science fiction have yet to be found.
We could be the only developed life form in the universe, or we could be the first to reach the stage of being able to send out waves, which would explain why we don't receive any. We might be the first. That would be a funny state of affairs. It's possible that a series of civilizations developed in the Milky Way, explored part of the environment, and then died out, never encountering or finding signs of another civilization throughout their existence. They experienced cosmic loneliness, but they weren't alone, at least temporarily. And that could be one of the possible answers to Fermi's paradox. Where is everybody? Well, they were here once, and maybe they will be again, but they're not around at the moment.
If this hypothesis is true, they have already visited us, but we weren't there. If this hypothesis is true, they will visit us, but we may not be here.
When it comes to stars in the universe, time is counted in millions and billions of years. So if extraterrestrial life exists for 100 or 1,000 years, there's every chance we'll miss it and never be contemporaneous with it. So the duration of a civilization's existence is very important. And given the way life is evolving on Earth today, driven by humanity, we can be pessimistic about this duration.
Beyond our ability to explore, if we are to nurture the hope of crossing paths with our successors, we need to be able to endure. Not for thousands, but for millions or even billions of years. And when we do meet them, here or elsewhere in the galaxy, what will we say to them?